Let's go back to high school, when we first learned what imaginary number is. Teacher said we define imaginary unit I as number whose square is -1. That is so weird, I said. -I is also a number which squares to give -1. Number that squares to give -1 is not unique, so the definition does not make sense. However, now I know this definition is not only appropriate but also beautiful because it is okay to call -I as I. In this video, we will see what on earth this means. Understand what isomorphism is and observe one application of it. There is a friend who is very good at math. Let's name her Math Girl. I'm jealous of her. That's why I casted an evil spell on her just before the complex number quiz. Let's draw a picture that shows her view. Because of the curse, she will recognize I as -I. Thus, she will recognize -I as -I, which is I. Will my evil plan succeed? Let's see. The problem of the quiz looks like this. Calculate 3 plus 4i, 1 minus 2i, plus 2 plus 7i. A. 13 plus 5i. B. 13 minus 5i. Pause the video, take out your pen and calculate. However, since Math Girl is casted to my spell, she will recognize the quiz differently. Calculate 3 minus 4i, 1 plus 2i, plus 2 minus 7i. A. 13 minus 5i. B. 13 plus 5i. Notice my answer and Math Girl's answer are the same. They are both A. My evil plan failed and Math Girl would not be able to notice that she was casted at all. When I was younger, my mom used to read science books to me. One day, she read, "Every animal sees the world differently. Insects view the world through compound eyes, and dogs view the world mostly in black and white," she read. Thinking a while, I asked, "Say an evil witch casted a spell to me so that I recognize real green as red and real red as green. I will not be able to notice that I'm cursed because you taught me color of an apple is called red and color of the grass is called green. Maybe I am under such curse." I may be under such curse, but there is no way to find out whether I'm under such spell or not. Thus, I think it is okay to say my view of the world and my mom's view of the world are equivalent. We are looking at the same world. This story is deeply related to a concept called private language argument of Wittgenstein. However, this is a math video, not a philosophy video, so let's stick on the topic. Back to the story of Math Girl and me. Since Math Girl can't know whether if she is under such curse or not, it is okay to say my view and Math Girl's view are equivalent. This is why it is okay to call -I as I. Here's a normal complex plane. And here's a flipped complex plane. Complex plane and upside down complex plane are equivalent. Let's analyze why Math Girl got her answer correctly more carefully. As the complex number written in the book passes the cursed eye, it changes into its complex conjugate. Mathematically, we can view the real world as domain, the world that Math Girl sees as codomain, and the cursed eye as a function that sends complex number a plus bi into its complex conjugate a minus bi. Famous properties of complex conjugate: it preserves addition and multiplication. Proving this is an easy exercise. Take out your pen and do some calculations. Now we know our function phi also preserves addition and multiplication. The reason why Math Girl got her answer correctly is because of these properties. Math Girl recognizes the input numbers like this. Remember the fact that Math Girl's I can be expressed as a function phi. To solve the problem, they both multiply first two numbers, then add the last number. We can simplify Math Girl's answer. By properties we saw before, Math Girl's answer can be changed like this. Since phi preserves multiplication and addition, phi 3 plus 4i, phi 1 minus 2i, plus phi 2 plus 7i equals to phi 3 plus 4i, 1 minus 2i, plus 2 plus 7i. Math Girl thinks the answer is this, but because of the effect of curse, the actual answer that she writes in the test paper is this, which is exactly same as my answer. Here are three properties that made Math Girl impossible to distinguish if she is cursed or not. First, phi preserves addition. In other words, phi z1 plus z2 equals to phi z1 plus phi z2 for all complex numbers z1 and z2. Second, phi preserves multiplication. In other words, phi z1 z2 equals to phi z1 phi z2 for all complex numbers z1 and z2. Third, there exists an inverse function of phi. Since you are watching a math video, I'm pretty sure you have heard the fact that there exists an inverse function if and only if the function is bijection. Mathematicians call function that satisfies these three conditions isomorphism, and the word equivalent as isomorphic. This is a formal definition of isomorphism. If S and S' are sets with addition and multiplication, isomorphism is bijection that preserves addition and multiplication. If an isomorphism exists, S and S' may be a different set, but the algebraic structure are the same. So, we can say S and S' are equivalent or isomorphic. Actually, there are many other definitions of isomorphism. Field isomorphism, vector space isomorphism, graph isomorphism, metric space isometry, topological space homeomorphism, differentiable manifold diffeomorphism, etc. All definitions differ a little, but the common concept is bijection that preserves the structure. Before we go to the final section, I have to admit I was using the words indistinguishable and identical in the same way. However, there are some mathematicians that say they do not mean the same. It is very surprising that we are so ignorant about what same and different means. However, the word isomorphic means indistinguishable and identical at the same time. I don't know the philosophical debate about whether this is an oversimplification or not, but this is the concept of isomorphic. Finishing the video with introducing an application will be nice. Homomorphic encryption is one of them. Encryption is a process converting an important information known as plaintext into a non-readable form called ciphertext. Encryption can be viewed as a function from set of plaintexts to set of ciphertexts. Decryption is a process converting a ciphertext into plaintext. Decryption can be viewed as an inverse function of encryption. Hackers should not be able to know what this inverse function is. Here's a situation when homomorphic encryption is needed. Say one company made an AI algorithm that, if patient's DNA information is entered, the probability of the patient getting diabetes in the future is calculated. Note that the algorithm is a complex sequence of a lot of operations like additions and multiplications. However, DNA information is very personal, so patient doesn't want the company to know it. Also, the company doesn't want people to know how their algorithm works, obviously. That's why patient want to make an isomorphism phi such that he or she knows phi and its inverse, but the company doesn't know the inverse. Instead of entering the DNA information directly to the algorithm, we can enter phi DNA information to the algorithm. If the output of algorithm pops out, we decode that output to get the probability of diabetes. If you remember, the algorithm is a sequence of operations, and remember the picture we saw before, you see this direct approach, and this indirect approach leads to the same result. This kind of encryption is called homomorphic encryption. Rigorously speaking, encryption is often a probability channel, not a function at all, and decryption is homomorphism, not isomorphism. However, we just ignore these complex details for simplicity. Isn't this surprising? This looks like a taxi driver that drives me to the destination without knowing my destination. This technology isn't used widely yet since it is too slow. However, if researchers find a fast way to compute this, we will be able to train artificial intelligence without actually accessing to private data. Now you understood isomorphism and its application properly. Thank you for watching.